Chapter 1.8, Inverse Functions. So in this chapter, we'll be defining an inverse, learning how to verify whether two functions are inverses of each other, how to find the inverse of a function, and then we'll be exploring what the graphs of inverse functions look like compared to each other. So first, the definition of an inverse function. So the function f with a superscript -1 of x is the inverse function to f of x equal to y if f superscript -1 of y equals x. So in other words, we will from now on not call it f superscript 1, we will call it f inverse. So f inverse of x is the inverse function to f of x equal to y if f inverse of y equals x. So in other words, the inverse function to f switches the output and input values. We can check whether two functions are inverses of each other by using composition. So remember from our previous chapter, when we compose two functions, we're plugging one into the other. So f inverse of f of x should come out to be just x, or the identity function. Similarly, f of f inverse of x should also come out to be that identity function. This is how we tell if two functions are inverses of each other, is by doing that composition. So it should work both ways. Really, if you check it one way, it should always work the other way no matter what. Like, that's just sort of how it works. But to really verify, to prove, you should be checking both directions. Both f of f inverse and f inverse of f. But notice that that identity function, that f of x equal to x, is very intrinsically linked with the inverse. Identities and inverses are, in general, very linked in algebra, throughout algebra. This is a concept you may have heard of if you took an algebra class recently. You would have heard of what the identity and the inverse are for multiplication, for example, or addition, how those are related to each other. So now we have an identity and an inverse for our functions. So this means that f to the -1, or f inverse of x, does not mean 1 over f of x. So this is one of the very common mistakes with this, is people see that -1 and think, oh, exponents. But that -1 exponent is, yes, an inverse, but it's an inverse with respect to multiplication. So you don't really need to think about that too deeply unless you're curious about exactly what it means to be an inverse versus identity, and how that is a really important concept in upper level mathematics. But for right now, all you need to really know is that f inverse of x is not the same thing as 1 over f of x, because that's just a notational thing for right now. So we can also note that a function only ever has one inverse, and because of that, we can say f inverse is the inverse of f, but f is also the inverse of f inverse, which is a weird sentence to say, but the point is this statement is essentially commutative. If a function has an inverse, then the inverse of that inverse gets us right back to the original function. Now, one more note to make is something we saw much earlier. Back in chapter 1.2, I introduced the concept of one-to-one functions. So we saw a one-to-one function was a function where all the y values are unique. So only one-to-one functions have inverses, and we'll see kind of why that is once we look at the graphs of our inverse functions later. But for right now, just note that one-to-one functions have inverses. Only one-to-one functions have inverses. But sometimes we can adjust the domain to make a function one-to-one just by cutting off the part that isn't. But how do we tell if it's one-to-one? So remember back to chapter 1.2 when I introduced this. And again, this was introduced earlier than your textbook introduces it, just so that you could see it at a time that when we talked about the vertical line test. Here, we're talking about the horizontal line test. So remember, the horizontal line test says that a function is one-to-one as long as every horizontal line you could possibly draw only ever hits one point on its graph. So the first For the first graph we have here is not 1-to-1, but the second one is. So the first graph does not have an inverse, at least not on its full domain, whereas the second one does have an inverse on its full domain. If I cut out part of this graph, if I just removed this and only made it this one side, it would have an inverse because it would then become 1-to-1. But as long as I am including the entire graph that's there, this is not a 1-to-1 function, so it does not have an inverse on its full domain. Now, for example, if we have f of x equal to 1 over x plus 2 and g of x equal to 1 over x minus 2, if I want to know is g equal to f inverse, or in other words, is g the inverse function to f, all I need to do is verify the following. F inverse of f of x should equal x, and f of f inverse of x should equal x. So in other words, I need to test g of f of x and f of g of x. If it's equal to x, if it simplifies down to just being that identity, I have an inverse function. So, first we're going to start with g of f of x. G of f of x equals 1 over x plus 2 minus 2. Okay, so I've plugged f of x into g of x right there. And then I'm going to simplify that. So remember 1 over x plus 2. So that is division by a rational function, or division by a fraction. So it's multiplication by its reciprocal. So that's going to simplify to 1 times x plus 2. Or in other words, 1 times x plus 2 over 1 minus 2. Then I simplify a little bit further to add that 2 to the negative 2 together, those cancel out, and I just get x. And so this is technically enough information to tell me whether or not this is an inverse. So yes, g is f inverse, and f is g inverse, but it's still good and generally expected for you to test both directions of it, mostly to make sure you didn't make a mistake. So if I test f of g of x as well, I'm going to get 1 over x minus 2 plus 2, which is 1 over x plus 0, because these two combine together, so plus 0, it goes away. Then, well, 1 over x is 1 times x over 1, which is just x. So it works that direction as well. So it should always work in both directions if it's going to work at all. So it's good to check your work by testing it f of g and g of f. But technically, having one of them is enough to say, yes, it is the inverse. All right, what about the domain and range of an inverse? So remember I said that inverse functions, the way they're related to each other is that you're essentially switching the outputs and inputs of the two functions. So the outputs of f are the inputs of f inverse and vice versa. So the range of f is the domain of f inverse, and the domain of f is the range of f inverse. So we just switch them around. We just take our domain and our range and we flip-flop them between the two functions. So in order to find an inverse, we may have to adjust the domain of f, since f inverse must be a function. So in other words, if our domain has some issue that would cause our f inverse not to be a function, in other words, we don't have a one-to-one function, but we can cut out part of the domain, we can then find a new inverse function based on that restriction. So for example, y equal to x squared is not 1-to-1 on its full domain, right? Y equal to x squared looks like this approximately. But if we restrict the domain to 0 to infinity, we can find its inverse. So restricting the domain means basically cutting off this part. So we now have just this part of it. And then I can solve to figure out what is its inverse. We will look at exactly how to figure that out in a moment. But the point is it is now 1-to-1. If I ignore this part of its domain, if I cut that out and I just say x squared on the domain 0 to infinity, then yes, it does have an inverse. So Here are some of the inverses of common functions and how we would have to restrict their domains in order to make sure those inverses are functions in and of themselves. So for example, the constant function really doesn't have an inverse. Technically, you can say it has an inverse of a single point, but we'd have to restrict it so far because there's really just no way to cut it down except to cut it down to that single point. Then, the identity, however, that one is a one-to-one function, right? We have the identity looks like this. So it's one-to-one, so we don't need any restrictions. Its inverse is just itself. The quadratic, on the other hand, again, like I said, we're going to cut out this half of the quadratic, and its inverse is then the square root. The cubic is one-to-one. Remember, the cubic looks not like that. Let's try that again. It looks something like that, and so it is one-to-one, and so we don't need to restrict its domain. Its inverse is the cube root. And then the reciprocal function, 1 over x, would have to be restricted to basically the domain it already has. It's already one-to-one, so we don't need to change its domain at all. We just know that we can't divide by 0. And its reciprocal is also, its inverse is also itself, so that's a special property of that reciprocal function. The reciprocal squared, on the other hand, we do need to cut out part of its domain, because remember, the reciprocal squared looks kind of like this, so it's not one-to-one. But if we cut off this side of it, then we get this one-to-one function, and its inverse is 1 over the square root of x. The cube root, on the other hand, is one-to-one. So cube root, remember, looks like this. It's one-to-one. We've already talked about the cube root's inverse was the cube. So same for the square root. Its inverse is x squared. But we do have to cut out part of the domain of x squared to say that. And then finally, the absolute value. We have a function that looks like this, so we're going to have to cut out one side of it to say, okay, we're only looking at 0 to infinity, and its inverse is also itself. So how do we find the inverse of a function? Here we were given, for the previous example, we were given two functions and asked to verify that they were inverses of each other or not. But most of the time you're not going to be given those two functions, you're going to be asked to find two functions. Or find the second function, find the inverse. So how do you do that? If we were given a table, one way we can do this is we're just inverting our table. We're switching our domain and our range. So a function f of t is given in the table showing distance in miles that a car has traveled in t minutes. And if we wanted to find and interpret f inverse of 70. So we can find the inverse by just switching the inputs and outputs. So t is now miles, and f inverse of t is now minutes. Yes, it's weird to call t miles, but for the context of the problem, we're going to leave it that way. So all I've done was I switched my domain and my range. So now it's, and now my x values or my t values are 20, 40, 60, 70 instead of 30, 50, 70, 90. Then the inverse, f inverse, tells us how many minutes have passed when we drive a certain number of miles. Remember, f of t said how many miles we drove after a certain number of minutes. It's all just about the interpretation, but essentially we get the same information. It's really just, what are we inputting here? If I give you a number of miles, you give me back a number of minutes. Instead of, I give you a number of minutes and you give me back a number of miles. So for tables, it's pretty easy to find the inverse because we just have to flip-flop at all the values. For graphs, it's also not too difficult, but there's continuity in here. There's a little bit more going on. So what we need to do is think about, well, what am I really doing? For the table, I am switching my x and my y values. That's essentially what's happening. So here, if I take a point on this graph and I switch its x and y values, or if I do that to every single point, that's how I would find the inverse graphically. So, to do that, what you're really doing is you are reflecting your graph over the line y equals x. So that's how to find the inverse graphically, is we reflect our graph over the line y equals x. So notice that 0.67 that I've identified, when flipped over y equals x, I get 7.6. That's what reflecting over that line does. So again, the identity function y equals x keeps coming back because it's very important, very related to how inverses work with each other. So that line here can allow us to find the graph of an inverse function even if we don't know what the equation was. And we just took everything and switched sides. But finally, the last way we need to be able to find an inverse, and the most common way, is using its equation. So if we're given a function, for example, f of x equal to 2 plus the square root of x minus 4, and we're asked to find the inverse, first, step 1 is make sure f is 1 to 1, and if it's not, restrict its domain. In this case, f is 1 to 1. You're just going to have to trust me on that, but it is 1 to 1. So there's no problem here. You can graph it to help yourself figure out if it's 1 to 1. That's the main way we know how to do that. So it is 1 to 1. Then, step 2 is we're going to replace f of x with y. So in other words, I'm just going to rewrite this, but write it as y equals 2 plus square root of x minus 4. So I haven't really changed anything. I'm just changing how I'm writing it. Now I make the change. I interchange x and y. In other words, I switch anywhere there was an x now becomes a y. Anywhere there was a y now becomes an x. There should only be one y there, but when we switch it around, we might end up with multiple y's in our new function. So x equals 2 plus square root of y minus 4. Now we solve for y. So to do that, I'm going to first subtract 2, so that'll be x minus 2 equals square root of y minus 4. Then I'm going to square everything to get rid of this square root. And so I'll have the square root of x minus 2 squared equals y minus 4. Then, finally, I get y equals x minus 2, all quantity squared, plus 4. So, the final step is just to rewrite it in function notation. Function notation being, we've identified an inverse, so we should use our inverse function notation, f negative 1 superscript, so f inverse of x is equal to x minus 2 squared plus 4. If you don't rewrite it in function notation, you will get points off, so make sure you're rewriting it in function notation. And then, just out of curiosity, if you wanted to know what the domain of this new function is, we would have to think back to what the domain of what the range of the original function was. Because remember, there's going to be a restriction on some of these new functions. So, f of x equal to 2 plus square root of x minus 4, if we think about, we know the square root function, looks like this, right? And then we have a horizontal shift. Minus 4 means we're moving this way, but that doesn't change the range. And then plus 2 means we're moving up, right? So we're like here. This is our function now. We moved up by 2 and to the right by 4. So our range is then 2 to infinity. I mean, our range is 2 to infinity, so our domain of f inverse, so this is range, is 2 to infinity. So our domain of f inverse is 2 to infinity. So even though the domain of this actual function, if I put that on a graphing calculator, the domain would be all real numbers. But I don't care about the whole function. I only care about how it is in relation to f. And so I have to cut down the domain to be the same as the range of the original function. Alright, and so that's it for our inverse functions. We just have one more chapter left in this unit, or in the home stretch now. Hopefully This one wasn't too bad. I know it's a bit shorter, and the last chapter is actually the shortest of all, so we're really winding down. Make sure, please, let me know if you have any questions about any of this, since we're getting closer to your exam. So make sure you are asking those questions and keeping up with all of the work.